All right, let's jump right back in. So we've discussed in the last video this area accumulation function and defined it for an arbitrary continuous function f of t, and we went and computed one, and we saw that the derivative of a of x ended up being f of t, or f of x, little f of x. And so here this established the following conjecture. We saw this worked for at least one function, so maybe this is a reasonable conjecture. For a continuous function f of t, let a of x be the area function for f of t with left endpoint a. So pick some a as a starting point. It's going to turn out not to matter because we're just looking at the derivative of it. Then the derivative with respect to x of a of x is little f of x. So this is our conjecture from that last problem. Let's see how we might go about seeing if this is true and proving it if it is true. So idea for proving this. We're trying to prove that the derivative of something is something else. And so we should look at what is the derivative with respect to x of a of x. And for this, we go back to the limit definition of the derivative. It's the limit as h goes to 0. H goes to 0 of a of x plus h minus a of x all over h. And so our idea here is to find some kind of estimate for a of x plus h minus a of x so that we can show in the limit that this turns out to be little f of x. So for this, I'm going to draw some pictures. So we're starting here. Here's my function f of t. It's some general function. It could dip below the t-axis. My a could be over in the negative. This is all going to turn out not to matter. This is just a general idea. So we want to get a hold of this value, a of x plus h minus a of x. So let's see here. A of x, big A of x, would be this area here. So this is my a of x. And then a of x plus h, maybe I'll sketch this in green, would be this area here, all of this area here. A of x plus h. So what is a of x plus h minus a of x? Well, it's the difference in the two areas. That is, we're investigating the change in the area function as x moves as x moves from x to x plus h. And so this area here, have I saved myself a color? Oh, not really. Maybe I'll just highlight it. This area here then is a of x. This is a of x plus h minus a of x. Now here's where I have to sweep a couple things under the rug here, but hopefully you'll understand the basic idea is that if h is really small, this area is going to look more and more rectangular. That is, if this difference between x and x plus h is very small, then the change in the function won't be very much, and so the top of the area will be roughly a horizontal line as I let h go to 0. So this a of x plus h minus a of x, this is approximately the area of a rectangle with height f of x and width h, right? The difference in these two is h. So this is approximately f of x times h. And as h goes to 0, this approximation is going to get better and better, and hence I can use it in the limit up there. So let's see. What happens if I replace a of x plus h minus a of x with this estimate we have f of x h? Oh, it's going to look pretty nice because it looks like some h's are going to cancel out. H goes to 0 of f of x times h all over h. The h's cancel out. I just get f of x. And that's exactly what I wanted to prove, that the derivative of the area accumulation function is exactly f of x. And so this is essentially the proof of the first part of the fundamental theorem of calculus. So let me say here, fundamental theorem of calculus, part 1, the derivative of a of x is f of x, where I've defined f of x, all these things up here. F is assumed to be a continuous function, left endpoint a. And notice that the fact that I had left endpoint a didn't matter. I could have moved this up. The most important part is the change in the function, and that's not dependent on my a. All of that area got removed when I computed this difference in the area. And so that's the first part of the fundamental theorem of calculus that tells us the derivative of a of x is equal to little f of x. Moreover, we can say a few more things here, that the area accumulation function, a of x, is continuous. Just in general. And differentiable. If we were able to compute the derivative, it must be differentiable. A of x is continuous and differentiable. And that this is its derivative. So I'll write this in an equivalent statement. So equivalently, a prime of x, derivative of my area accumulation function, is the derivative with respect to x of a of x, which is the definite integral from a to x of f of t dt. So this is an important way to write this, is that the derivative of a definite integral, where my right endpoint is variable, and I take the derivative with respect to that variable, gives me exactly little f of x. The most important part of this is the connection. Again, I want to answer this motivating problem that I introduced in the first part of this video, is what is the connection between the definite integral and the antiderivative, or the family of antiderivatives? And so what this is telling me, since the derivative of the area accumulation function is little f of x, what this is telling me is that a of x, so I'll say in particular, a of x is an antiderivative for f of x. And so that is pretty neat. We have found explicitly what an antiderivative for f of x is. It's this area accumulation function, and that's pretty cool. So that answers part 2, the motivating problem number 2 of this connection between antiderivatives and the definite integral. To answer part 1 of those motivating problems, watch the next video.